let me quickly recall that in the previous lecture we defined the evaluation or the substitution map from the ring of binomials to another ring by essentially evaluating the binomials at a particular element of the target ring. We denoted this by phi sub b. It's not a God-given notation. We are using it for this course. So what is phi sub b? Phi sub b, when we give it a binomial f, it just evaluates it at the small element, at the small b, at the element small b. So phi sub b of f of x is substituting b for x, so it's f of b. So that's the definition of phi sub b. We discussed that kernel of phi sub b is precisely the set of all the binomials with coefficients inside A that have b as a 0. This is a connection between the historical point of view towards algebra understanding, zeros of binomials, and ring theory. And image of phi sub b, as we will see, is precisely the smallest subring of capital B that contains both the ring A and the element B. Point out, let's recall that elements of the image consist of elements of the form. So I give it a binomial, a sub 0 plus a sub 1x plus dot 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 a sub n x to the n, and then I substitute b for x, and I end up getting that it is a sub 0 plus a sub 1b plus a sub n b to the n. So that means the elements of the image consists of elements of this form, where a sub i's are arbitrary elements of the ring capital A, and n is an arbitrary positive integer. Now, in particular, so you see, I want to show that image of phi sub b is a subring. That's for sure, because phi sub b is a ring homomorphism, and it contains capital A, and it contains B. Why does it contain every element of the ring capital A? By just focusing on constant binomials. So essentially here a sub 0 can be anything, and I can drop the other terms. So you can think about constant binomials in order to get that every element of the ring A is inside the image. Now, how about B? I can think about the binomial x. When I substitute b for x, this is sent to B. So B is inside the image, and every element of the ring A is inside the image. So we end up getting that the image of phi sub b is indeed a subring that contains both A and B. Now, why is it the smallest such subring? So we pick an arbitrary subring that contains both capital A and B, and we need to show that image of phi sub b is a subring of such a ring. So we pick an arbitrary element of the image. That means I'm picking a sub i's inside the ring capital A, and I have to show this linear combination of 1b, b to the n with coefficients a sub i's is inside S. But that's for sure, because S is closed under addition and multiplication. So this means when I multiply b by itself n times, because b is inside S, b to the n is inside S, b squared is inside S, and so on. And then I can multiply it by a sub i's, because a sub i's are also inside S. So they will be inside these products, these terms will be inside S. But now S is closed under addition, so their summation is inside S. So we deduce that every arbitrary element of the image of phi sub b is also inside S. Therefore, image of phi sub b is a subring of S. So altogether, we deduce the claim that image of phi sub b is the smallest subring of capital B that contains both the ring A and the element small b. Okay, now this smallest subring is denoted by A bracket B. So we denote it by A bracket B. There is a kind of warning that I have to say, because I've seen students make mistake and get confused, and they confuse this notation with the notation of ring of binomials. That's for a good reason, right? So ring of binomials is also denoted by a similar notation, A bracket X. The only, the important difference between them is the fact that X is an indeterminate, but B is an element of the codomain of the ring capital B. So that's the main difference between them. So if B is an element of a given ring, then A bracket B denotes the subring, the smallest subring that contains both A and that element. If B is an indeterminate, then A bracket B denotes the ring of binomials with coefficients inside A and indeterminate, whatever variable we've been choosing. Okay, so that's a warning that I wanted to raise. Please pay attention to that. And the other thing is that by the discussion that we had, we already know that image of the evaluation map or the substitution map is nothing but the smallest subring that contains both A and the element B. Okay, and for the discussion and problem session, I encourage you to think about the following problem. Remember that when we were talking about Q bracket I, we wrote it as the set of the elements of the form A plus BI, where A and B are rational numbers. When we were talking about Q bracket root 2, we wrote A plus B root 2, where A and B both were rational numbers. This means for these rings, we do not need the entire ring of binomials. We can focus only on binomials that have degree at most 1. So those are enough in order to give us the entire Q bracket I or Q bracket root 2. For Q bracket third root of 2, you realize that we need to work with A plus B times the third root of 2 plus C times the third root of 2 squared. But we do not need to go further. So here we only need binomials that are of degree at most 2. Now, the question that I want to ask you, and I'm asking you to think about for the discussion and problem session, is what is the general rule? What do you think is the general rule for A bracket B? Do we always need all the ring of binomials, or under what circumstances can we go smaller? Can we restrict ourselves to certain degrees, and so on? So think about this question. Okay, now let's go to the next topic, and that's units. So what are units? Let's recall that I started the whole thing by saying that Khwarizmi started algebra by studying linear and quadratic equations. Let's start with linear equations now, but try to do it for an arbitrary ring. What do I mean by that? Can we solve the equation AX equals to B in a given ring R? Of course, over complex numbers or real numbers, as soon as A is not 0, I can multiply both sides by A inverse. I end up getting that X is A inverse B is the unique solution of such linear equation. But what about an arbitrary ring? So we see that if A has a multiplicative inverse in this arbitrary ring, we can repeat the same argument. That's a motivation to define, to call such elements a special name. So we say an element of a unital commutative ring is a unit if it has a multiplicative inverse. And that means if I can find some element of this ring that I can multiply A by and end up getting the identity of the ring. So if I can multiply A by some element of the ring A prime and end up getting 1, then we call such element a unit. the set of all the units is denoted by A subcross. Okay, so we denote this by A subcross, and then let's make it a bit more concrete in the following sense. That I'm here saying if there is a multiplicative inverse, but as we've learned in group theory, if there is such a thing, it should be unique. Let's recall the proof of that statement. So suppose I give you a unit in a ring. Next, we want to show that there is a unique multiplicative inverse for this. So suppose, and this multiplicative inverse, as in group theory, is denoted by a to the power -1. So to show that, let's assume that there are two of them, a prime and a double prime. That means I'm assuming a times a prime and a times a double prime, both of them are identity of the ring, and I want to show that a prime is a double prime. So we start with a prime. We say a prime is nothing but 1 times a prime. That's because 1 is the identity of this ring. Next, we write down 1. Instead of 1, I'm going to use the fact that a times a double prime is supposed to be identity and write it as a times double prime, a double prime. But I also notice that it's commutative, so I can flip the order. So I write it like this. Next, I use associativity. Associative. And reorder the parentheses. Then a times a prime is identity. So I rewrite it. Instead of this, I write identity. And now a double prime times identity is a double prime, and I deduce that a prime is, in fact, a double prime. And that shows that these two are the same, so I have a unique multiplicative inverse. From this point on, this unique multiplicative inverse is denoted by a to the power -1. Okay, so if it has a multiplicative inverse, it's unique. Now, next we see that, in fact, the set of all the units form a group under multiplication. No matter what ring is, I'm going to get a group out of it. So let's see why this is the case. In order to show a set and a potential operation is a group, first I need to show that it is indeed an operation. In this case, I have to show that a cross and multiplication, a cross is closed under multiplication. Next, I need to show that my operation has the associativity property. Then I have to discuss why there is a neutral element. And finally, I have to discuss why every element has an inverse. Okay, let's start with the first one. Why is it closed under multiplication? This means I have to pick 2 units inside this ring, and then I have to argue that their product is also a unit. But it is rather easy. Let's repeat the argument from group theory. Knowing that A and B are units, this means they have multiplicative inverses, A inverse, A to the power -1, and B to the power -1. Now, as in group theory, we do know that the inverse of AB should be B inverse times A inverse. So I just multiply AB by B inverse times A inverse. Notice that B inverse and A inverse, both of them are in the ring. Ring is closed under multiplication, so their product is also inside the ring. Now, by using associativity, one can easily see that this product is, in fact, identity. This means I can multiply AB by some element inside the ring and get 1. Therefore, A times B is a unit. Okay, good. So it's closed under multiplication. Next, I have to argue why my operation, which is multiplication here, is associative. We have it for free because the ring A, in the ring A, multiplication is associative. So associativity we have for free. Now, why do we have the neutral element? The candidate would be the identity of the ring A. The point is that the identity of the ring A times itself is 1. So this means it's a unit inside the ring, because I can multiply it by something and get 1. So it is a unit. Good. It is inside the units of this. And why is it the neutral element? Because when I multiply it by everything, I end up getting that element back. So it is, this means that the set of units do have neutral elements under multiplication. Now, why do we have inverse? So it seems redundant because units by definition have multiplicative inverse. The only thing that I have to say is that by definition, the inverse belongs to the ring, not necessarily inside A cross. I have to argue why A inverse is also a unit, but that's easy because A times A inverse is identity, it's commutative. So A inverse times something is identity, and that means A inverse is also a unit. So we show that every element has an inverse inside the set of units, therefore the set of units form a group. Now let's try to understand this group in certain examples. If I look at the rational numbers, every non-zero element has an inverse. So the group of units of rational numbers is the set of all the non-zero elements. The same is true for real numbers and complex numbers. So one might get tempted and say, maybe it is true for every ring, that every non-zero element is a unit. But as soon as we look at integers, we see that it's not correct. So let's try to understand what is the group of units of ring of integers. So A, an integer, is a unit inside the ring of integers means what? It means I can multiply A by something within a ring of integers. So there exists A prime in ring of integers such that their product is 1. Now, because their product is 1, neither can be 0. So this means I'm multiplying two integers and I'm getting 1. Now, if I take absolute value, I end up getting that product of two positive integers is 1. But positive integers are at least 1. So product of two integers that are positive is 1, but both of them are at least 1. This means both should be 1. So we deduce that the absolute value of A is 1. This means A has only two possibilities. It's either positive 1 or negative 1. Now notice that both of them are indeed units. 1 times 1 is 1, and negative 1 times negative 1 is 1. So both of them are units, and altogether we deduce that the group of units of ring of integers consists of two elements plus 1 and negative 1. You see, it's very restrictive for ring of integers, unlike ring of rational numbers or real numbers or complex numbers. How about units of ring of integers mod n? What can we say about units of ring of integers mod n? Let's start with an example. What is inverse of 2 inside z sub 3 if there is such a thing? Okay, what does that mean? What does it mean that we are looking for an inverse of 2? This means we are looking for some element inside z sub 3 that's a multiplicative inverse of 2 in z sub 3. Please do not write 1 over 2. So 1 over 2 is a rational number. Elements of z sub 3 are residue classes. So they are equivalence classes within integers. So our answer should be an integer or a residue class represented by an integer. So this means we are looking for some element inside z whose residue class times 2 is 1 mod 3. This means we are looking for a solution for the congruence equation 2x congruent to 1 mod 3. Notice that 2 is negative 1 mod 3. And now it's easy to see that negative 1 times negative 1 is 1. Therefore, 2 times 2 is 1 mod 3. So this means 2 is a solution for this. And as we've discussed, if such an equation has a solution, it's unique. And that's the multiplicative inverse. So the multiplicative inverse of 2 is nothing but 2 in z sub 3. Okay, now we want to use the same logic in order to understand the entire, the set of units of ring of integers mod n. So a residue class, bracket A, is a unit if and only if it has a multiplicative inverse. So this means if and only if I can find some integer x such that a times x is congruent to 1 mod n. What does that mean? This means n should divide ax minus 1. What does that mean? This means ax minus 1 should be a multiple of n. So this means I need to be able to find x and y, integers, such that ax minus ny is 1. Alternatively, I can say that this happens precisely when 1 belongs to a multiple of a plus a multiple of n. Now, you've seen this in either your number theory course or 109 or your group theory course, that multiples of a plus multiples of n is precisely multiples of the greatest common divisor of a and n. So that means 1 belongs to the set if and only if the greatest common divisor of a and n is 1. Now altogether, this implies what? This means the residue class represented by a is a unit in the ring of integers mod n if and only if a and n are coprime. So let's summarize it in the following sentence, in the following theorem. So this is what we said, that the group of units of ring of integers mod n consists of residue classes that are represented by integers that are coprime with n. Now, this means in particular the cardinality of this group is precisely the number of integers from 1 to n that are coprime with n. This number is denoted by phi of n, and this function is called Euler function or Euler's phi function. So it is sometimes called Euler's phi function. Now we can immediately prove Euler's theorem in classical congruence arithmetic. So what does the statement say? It says that if a and n are coprime, both of them are integers, if they are coprime, then a raised to power phi of n, where phi is the Euler's phi function, is congruent to 1 mod n. This is a very interesting congruence relation. So even the case when n is a prime number, this is an interesting result, and it's often called Fermat's little theorem. So you can use this to show the following, that if p is prime, then a to the p is congruent to a mod p. Think about it, why this is the case, and we can discuss it in the discussion and problem session. But for now, let's prove Euler's theorem. So we are going to use group theory in combination with what we've learned about units of ring of integers mod n in order to prove this congruence relation. So in group theory, you've learned that if I give you a finite group and an arbitrary element, small g, of this finite group, capital G, then g raised to the power of the cardinality of the group is always the neutral element of the group. So g, small g, to the cardinality of the group is always identity of the group. Now, we are going to use this for the group of units of integers mod n. Knowing that a and n are coprime, we do know that the residue class represented by a is actually a unit inside the group of integers mod n. And therefore, when I raise it to the cardinality of this group, I get the identity of this group. In the language of congruences, it means that a raised to the power of the Euler's phi function of n is 1 mod n, and that's exactly what we wanted to show. You see a cool application of what we learned. But let's go back to our kind of misleading examples of rational numbers, real numbers, and complex numbers. In those examples, any non-zero element was a unit. But immediately we saw that in integers, this is not the case. But it seems that these kind of rings deserve a name, because in those kind of rings, we can solve every linear equation quickly. Ax equals to b always has a unique solution if a is non-zero and every non-zero element is a unit. So we call such a thing a field. Let's make it formal and add all the needed conditions. So a unital commutative ring is called a field if the set of units is precisely all the non-zero elements. You see, there is a hidden extra condition in this statement, and the hidden condition is that, you see, 1 is always a unit. I'm saying the set of units is supposed to be f minus 0. In particular, I'm saying that in a field, 1 is not 0. So this means f cannot have a single element. F should have at least 2 elements. This is a subtle hidden condition in this statement, in this definition. So the set of units should be precisely f minus 0. In that case, if f is unital commutative, we call it a field. And rational numbers, real numbers, complex numbers are examples, and integers is a non-example. Integers is not a field. Now, how about ring of integers mod n? By this discussion, we understand the group of units. The group of units consists of those elements that are co-prime to n. Now, if it's supposed to be a field, this means every non-zero element should be co-prime. This means if I look at numbers from 1 to n, everything besides n should be co-prime to n. That's exactly saying that n is prime number. So let's write it down and summarize it. So for a positive integer, z sub n is a field if and only if n is a prime number. So z sub n is a field if and only if n is a prime number. The only subtle thing that I have to add is that we have to exclude n equals to 1. So again, because this is a field, implies that it should not be the trivial group. Z sub 1 is the trivial ring, not the trivial group. So Z sub 1 has only one element, that's 0. So it cannot be a field. And it is not prime anyway. Now, for numbers more than 1, then I can say what I just mentioned, that Z sub n is a field precisely when all the numbers from 1 to n minus 1 are co-prime to n, and that means n is prime. Now, let's go back to the linear equation ax equals to b, but let's look at a particular one, ax equals to 0. So over complex numbers, as soon as a is not 0, it has a unique solution, and that's x equals to 0. But in z sub 4, in z sub 6, these are not, 0 is not the unique solution. In fact, 2 times 2 is 0 in z sub 4, or 2 times 3 is 0 in z sub 6. So again, there is a distinction between what we used to and an arbitrary ring. So in order to be able to rely on our intuition, we have to define some properties for the ring, for the elements of the ring, and so on. In a unital commutative ring, we say an element A is a zero-divisor. So we say A is a zero-divisor if, first of all, it's not 0, and second, A times something non-zero ends up being 0. So if ax equal to 0 has a non-zero solution, then we say A is a zero-divisor. So it is crucial that this B is non-zero. If I manage to find a non-zero solution for ax equal to 0, then we say A is a zero-divisor. And the set of all the zero-divisors of A is denoted by D parentheses A. This notation of D parentheses A is not so standard. It differs from lecture to lecture, not within our course, but different instructors might use different notation. I'm borrowing this notation from the book by T.N. McDonald, which is a famous book on commutative algebra. Anyway, so D of A in our course denotes the set of zero divisors of the ring A. Now, if I do not have any zero divisors, these are a special kind of rings, and we call them integral domains. But let's be precise. If it's unital commutative, it should be unital, it should be commutative. Again, let me repeat that in this course, we are focusing on unital commutative rings. We do not work with non-commutative rings at all. So if A is a unital commutative ring, we call it an integral domain if, first of all, it's not the trivial ring, meaning it has at least 2 elements. Again, meaning it means that 0 is not 1. So why 0 is not 1 is the same as saying that we have at least 2 elements and so on. We can discuss it in the discussion and problem session. It's easy. I encourage you to think about it. So that's the first condition. 0 should not be 1. And second, more important condition, we should not have any zero divisors. So no zero divisors and non-trivial ring add up, giving us what we call an integral domain. Okay, examples: ring of integers, rational numbers, real numbers, complex numbers. These are all integral domains. Non-examples: Z sub 4, ring of integers mod 4, ring of integers mod 6. These are not examples. As we see, as we've discussed, 2 times 2 is 0, 2 times 3, 2 times 2 is 0 in Z sub 4, and 2 times 3 is 0 in Z sub 6. But neither 2 nor 3 are 0 in Z sub 6. In general, what is the connection between zero divisors and units? There is no, they have nothing in common. So something that's unit can never be a zero divisor. And it's not surprising, because I've discussed it, I started discussing them in terms of linear equations, and we said that if A is a unit, then AX equals to B, no matter what B is, has a unique solution. In particular, AX equal to 0 has a unique solution. But on the other hand, A is a zero divisor if I have a non-zero solution for AX equals to 0. So that's the proof. But you can also look at this line of argument, suppose to the contrary, that an element A is both a unit and a zero divisor. And that means that I can find something non-zero. I can find something non-zero and multiply it by A, end up getting 0. But then you can multiply both sides of this by A inverse times this, A inverse times this, A inverse times the left side cancels out A, I get B. A inverse times 0 is always 0. So we end up getting that B should be 0, which is a contradiction because we just said that B is not 0. So altogether, we deduce that a unit is never a zero divisor. Now, if every non-zero element is a unit, this means we do not have a zero divisor at all. This means we have an integral domain. What kind of ring has this property that every non-zero element is a unit? Yes, fields. So this means that we are showing that every field is an integral domain. There is this subtle other condition about non-triviality. Both of them satisfy this. So I encourage you to think about this non-triviality condition as well. But again, what did we prove? We showed that every field is an integral domain. How about the converse? Is every integral domain a field? Of course not. Ring of integers. Ring of integers is an integral domain, but it's not a field. So the converse is not correct in general. What we will show next is that in the finite ring case, the converse is correct. So we will show that a finite integral domain is indeed a field. But before doing so, let me show an important property of integral domains that's called cancellation law. So what is the cancellation law? If D is an integral domain, so D is an integral domain, then if I give you a non-zero element, A, the following holds. If I tell you AB equals to AC, I can cancel out A's and deduce that B is C. So we often write down that we write AB equals to AC and cancel it out. Yeah. So if AB equals to AC and A is not zero, then I can cancel it out, and that's called the cancellation law. Why is that the case? It's a simple algebra. So we subtract AC, or we add a negative AC to both sides. We deduce that AB minus AC is 0. Then we use distribution law and factor out A. We deduce that A times B minus C is 0. A is not 0. A is not a zero divisor, so I cannot multiply A by something non-zero and get 0. That means B minus C should be 0, which is the same as saying that B is C, and that's exactly what we wanted to show. So cancellation law is an important property of integral domains. In fact, one can show that a non-trivial ring is an integral domain if and only if it satisfies the cancellation law. And the other direction, I leave it for you to prove. Now let's go to what I promised. So if D is a finite integral domain, then it's a field. So in the infinite case, ring of integers is an integral domain, it's not a field, but in the finite case, it is the case. Let's think about it. Let's go backward argument and try to actually prove it. So D is an integral domain. So in order to show something is a field, I have to show you it's a unital commutative ring, and the set of units is precisely D minus 0. But D is an integral domain, so automatically we know that it's a unital commutative ring. And in addition, we also know that it's non-trivial. So that means it's enough to show every non-zero element is a unit. So that's our target. We pick a non-zero element A, and I want to show it's a unit. That means, again, what? It means I need to show if A is non-zero, the equation AX equals to 1 has a solution inside the ring D. Let's reinterpret this in terms of a function. Let's call the function L sub A to be the multiplication by A. This is in the spirit of Cayley's theorem in group theory, if you remember. So in Cayley's theorem, it says what? It says that every group can be understood as a permutation group. And the way to show it is by allowing every element to be multiply the entire group by a given element. So we are doing the same thing here. So we are multiplying the ring D by the element A. And we are calling this the function L sub A. Now, saying that I want to say AX equals to 1 has a solution in D is the same as saying that we want to show 1 is in the image of L sub A. So our target at the moment is to show that 1 is in the image of L sub A. But we'll show a stronger result. We show that L sub A is indeed surjective. So everything inside D will be in the image of L sub A. So our target is to show that L sub A is indeed surjective. But here is the critical point that finiteness of D comes to the picture. Notice that L sub A is a function from this finite set D to itself. Now, Pigeonhole Principle says that if I have a function from a finite set to itself, it is surjective if and only if it is injective. Okay, let's try to understand this. If it's not surjective, it means, if you think about these guys as pigeons, the elements of the domain as pigeons, and think about the elements of the codomain as pigeonholes. So we are assigning pigeons to these pigeonholes. Now, if it's not surjective, this means one of the pigeonholes will be empty, but they have the same cardinality. This means I have less number of pigeonholes as pigeons. So two of them should share a pigeonhole. That's Pigeonhole Principle. That means this cannot be an injective function. So if it's not surjective, it cannot be injective. And the other side, it has a similar kind of flavor. But we are focusing on this side because this is the direction that we want to go. So what I'm saying is that it's enough to show this function is injective. Okay, so I want to show that it's injective. What does that mean? This means if the value that this function gives me at b and c are the same, then I have to say b and c are the same. But L sub a of b is a times b, L sub a of c is a times c, a is not 0, so I can use cancellation law, and I deduce that b is indeed c, and that's exactly what we wanted to show. So altogether, we deduce that L sub a is injective, therefore it's surjective, therefore 1 is in the image, and that means ax equals to 1 has a solution inside D, which means a is a unit, and that finishes the proof. So every finite integral domain is a field. So next we want to discuss what is characteristic of a ring. Notice that, if I give you a ring, if I forget about the multiplicative structure and just use the additive structure, the group structure, that can be a very good start to characterize, to be able to characterize a ring. So far I was talking about the multiplicative structure, the units, and so on. Often that's harder than the additive structure of a ring. Okay, what do I mean by that? What can we do about the additive structure? I can start with an element and start adding it to itself, and so on. And I can ask myself, what is the additive order of this element? This means, do I get to 0 after adding it n times? Can I find an n that works for all the elements of the ring at the same time? So let's put all such possible positive integers in a set, and let's call it n sub plus of a. And this plus stands for the addition structure, for the addition of this ring. So n sub plus of a is the set of all the positive integers that kill all the elements of the ring. That means when I add every element of the ring n times, I end up getting 0. This set can be empty. If this set is empty, we say that the characteristic of A is 0. If this set is not empty, then by the well-ordering principle, it has a minimum. So this way we can define characteristic of a ring. The characteristic of a ring is 0 if this set is empty, and it is the minimum of this set if it is not empty. So this is how we define the characteristic of this ring. Let's put it in perspective of the additive structure of the ring and the ring homomorphism E that we've defined earlier in the previous lecture. So recall that we used additive group structure of A in order to define this ring homomorphism from ring of integers to every unital commutative ring, and that is E of n being n times the identity of the ring. We showed that it is indeed a ring homomorphism. Now, the tight connection between this special ring homomorphism and the characteristic of the ring A comes from the next lemma, which says that kernel of this ring homomorphism is precisely multiples of the characteristic of the ring A. So kernel of this ring homomorphism is precisely multiples of the characteristic of A. Let's see why this is the case. Of course, I'm working under the assumption that the ring is unital and commutative. So first notice that kernel of E is a subring of integers, it's a subgroup of integers. And in group theory, you've learned that subgroups of Z consist of multiples of a given integer. So every subgroup of Z is of the form n naught Z for some integer n naught. So for some non-negative integer n naught. So suppose kernel of E is n naught Z for n naught that's non-negative. And I'm going to split it in two cases. So either n naught is 0 or n naught is not 0. So let's start with the case that n naught is 0. So suppose n naught is 0. That means what? And I'm assuming that means I'm assuming that kernel of E is 0. So in group theory, you know that kernel is 0 if and only if the group homomorphism is injective. Here I'm not going to use it, but it's good to recall this. If you don't remember it, go and review your group theory part. So kernel of a group homomorphism is 0 if and only if the group homomorphism is injective. Review this part of your group theory. But let's come back to this argument. So the case 1 implies that kernel is 0. That means there is no positive integer n such that n times identity of the ring is 0. Now, what was n plus a? N plus a was asking what are the positive integers that kill all the elements. In particular, they should kill the identity. If there are no positive integers that kill identity, so this set is empty. So this n plus a should be the empty set, and therefore, by definition, the characteristic of a is also 0. So this means we get the claim. We get that kernel is 0, characteristic is 0, so multiples of zeros are just 0, and we get the equality. Now, suppose, let's go to the second case, suppose n sub 0 is not 0. When n sub 0 is not 0, then what? Then first I am going to show that every element of n plus a is at least n naught. Why is that the case? If I give you n inside n plus a, by definition, every element of a times this is 0. In particular, we have this for identity, but that means n belongs to the kernel. That means n is a multiple of n naught. Assuming that it's positive, we deduce that n naught is less than or equal to n. Okay, so this means n naught is less than or equal to the minimum element of n plus that, and that is the characteristic. Now I want to go the other way. Knowing that what does it mean? My next step is to show that in fact n naught itself is an element of n plus a. So this means I want to show n naught times every element of the ring is 0. Let's start with knowing that n naught times identity is 0. That means when I add identity and naught times, I'm getting 0. Now multiply both sides by arbitrary element small a of the ring and use distribution property and the fact, so use distribution and the fact that a times identity is a. So using these two, we can deduce that it is a plus a plus a, and so n naught times a is 0. That means n naught is inside n plus of a. And that finishes the proof, because this shows n naught is at least the minimum. But now, knowing that n naught is at least the characteristic, and earlier we showed that it is at most the characteristic, so both together imply the claim that n naught is precisely the characteristic, and therefore we get the claim. Let me finish today's lecture by showing that characteristic of an integral domain is either 0 or a prime number. So we connect these two parts of the course as well. So integral domains and characteristics. Okay, so notice that so I'm going to assume that characteristic is not 0. Because D is an integral domain, it's not a trivial ring, so 1 is not 0. That means the characteristic is not 1. You see, if characteristic is 1, this means every element is 0. Then it's a trivial ring. That altogether, this means I'm assuming characteristic of D is an integer that is more than 1. Now, if it is not prime, then I can write it as A times B, where both A and B are integers more than 1 and strictly less than characteristic. Now apply our ring homomorphism E. So E of AB is 0, but it's a ring homomorphism, so it is E of A times E of B. We have no zero divisor, so if E of A times E of B is 0 in this ring, then one of them should be 0. So it's either E of A is 0 or E of B is 0. But then that means either A is inside the kernel or B is inside the kernel. But that's not possible because kernel consists of multiples of AB, and A and B are numbers more than 1. So A cannot be a multiple of AB, considering A and B, both of them are more than 1. Okay, so we'll continue the next lecture.